Two half cylinders of diameter 16 meet at a right angle in the accompanying figure. Find the volume of the solid region common to both half cylinders. So what we are looking for is the volume of this region that is shaded green. The key to this problem is to draw an accurate representation of one of these sections. And when I say one of these sections, I mean break it up into four parts. We would have one that would occur here in the first quadrant, one in the second, one in the third quadrant, and one in the fourth. So this drawing came from Stack Exchange and I think is very well done. And it shows that we have an x-axis, a y-axis, and then a vertical z-axis to make this a three-dimensional figure. And it shows that the cross-section of one of these solids would be this shaded area here that would form a square. Then we could imagine that this shaded region could have some thickness applied to it, and it would become a volume. The thickness would be vertical along the z-axis, so we would call that a delta z. And if I were to draw that in 3 dimensions, one side of the square has been called A, so another side would also be A, and then the thickness would be delta z. So the volume of this would be A squared delta z. Now we need a relationship between A and Z because apparently Z is going to be our variable of integration. So let's draw a line that will extend from the origin out to the point where this cross-section meets the arc of the half cylinder. If we were to look at this vertical and then along the x-axis to the origin, and then our line that we drew from the origin out to that point on the arc, we wind up with a right triangle. So let's draw that over here where we can analyze it a bit. So we have a right triangle that has an altitude of z. This leg would be A, and the hypotenuse would be the radius of one of those half cylinders. And we can see that we can apply the Pythagorean theorem. So we have a squared plus z squared equals r squared. Now r will be a constant because we will have a specific diameter on these half cylinders. Now let's solve for a in terms of z. So we would have a squared equals r squared minus z squared. We have a formula for a volume, and we'll call this V sub I. The volume of any of these rectangular solids that we would encounter as we go from the bottom of this section, which would lay on the xy axis, all the way up to the top. That volume would be a squared delta z, or in other words, r squared minus z sub I squared times delta z. We could approximate the volume of the entire solid with a sum, I equals 1 to n, r squared minus z sub I squared delta z. That would be an approximation. The actual volume we then could express as a limit as n goes to infinity of the sum, I equals 1 to n, r squared minus z sub I squared delta z. But this would be an integral. And we would need to determine what the limits of integration would be. Now, what we need to do is decide, well, where does this stacking begin and where does it end? So from the bottom to the top, the stacking would start laying on the xy plane where z would be 0. And then it would continue on up to where z would be equal to the radius of these half cylinders. So in order to express this then as an integral, we would have the volume equal to the integral from 0 to r, the radius of the half cylinders, r square minus z square dz. Integrating this, we would have r square z, remember r is constant, z is our variable of integration, minus 1/3 z cubed evaluated from 0 to r. This would be r cubed minus 1/3 r cubed minus 0, which would give us 2/3 r cubed. Now let's remember that we found the volume of one of these sections. There are 4 when we have half cylinders intersecting. So the volume then for this entire solid would be 4 times this volume that we found for just one section. So that would be 8/3 r cubed. We are told that the diameter of these half cylinders is 16. So that means then that the radius would be 8. So to find this volume then, we would say the volume is equal to 8/3 times 8 cubed, or 4,096/3.